let's see if we can learn a thing or two about the hyperbola. Hyperbola. And out of all of the conic sections, this is probably the one that confuses people the most because it's not quite as easy to draw as the circle and the ellipse because you got to do a little bit more algebra. But hopefully over the course of this video, you'll get pretty comfortable with that, and you'll see that hyperbolas in some way are more fun than any of the other conic sections. So just as a review, and I want to do this just so you see the similarity in the formulas or kind of the standard form of the different conic sections. If you have a circle centered at 0, its equation is x squared plus y squared is equal to r squared. And we saw that this could also be written as, and I'm doing this because I wanted to show that this is really just the same thing as the standard equation for an ellipse. If you divide both sides of this by r squared, you get x squared over r squared plus y squared over r squared is equal to 1. And so this is a circle. And once again, just as a review, a circle, all of the points on the circle are equidistant from the center. Or in this case, you could kind of say that the major axis and the minor axis are the same distance, that there isn't any distinction between the two. You're always an equal distance away from the center. So that was a circle. An ellipse was pretty much this, but these two numbers could be different because your distance from the center could change. So it's x squared over a squared plus y squared over b squared is equal to 1. That's an ellipse. And now you'll see that and I'll skip parabola for now because parabola is kind of an interesting case and you've already touched on it. So I'll go in more depth in that in a future video. But in a hyperbola is very close in formula to this. And so there's two ways that a hyperbola could be written. And I'll do those two ways. So it could either be written as x squared over a squared minus y squared over b squared is equal to 1. Notice the only difference between this equation and this one is that instead of a plus y squared, we have a minus y squared here. So that would be one hyperbola. The other one would be if the minus sign was the other way around. If it was y squared over b squared minus x squared over a squared is equal to 1. So now the minus is in front of the x squared term instead of the y squared term. And what I want to do now is try to figure out how do we graph either of these parabolas. And maybe we'll do both cases. And in a lot of textbooks, or even if you look it up over the web, they'll give you formulas. But I don't like those formulas. One, because I'll always forget it, and you'll forget it immediately after taking the test. You might want to memorize it if you just want to be able to do the test a little bit faster. But you'll forget it. And the second thing is, not only do you forget it, but you'll probably get confused because sometimes they always use the a under the x and the b under the y, or sometimes they always use the a under the positive term and the b under the negative term. So if you just memorize, oh, a divided by b, that's the slope of the asymptote and all of that, you might be using the wrong a and b. So I encourage you to always kind of reprove it to yourself. And that's what we're going to do right here. And it actually doesn't take too long. So these are both hyperbolas. And what I like to do whenever I have a hyperbola is solve for y. So in this case, I get, let's see, if I subtract x squared over a squared from both sides, I get, let me just change the color, I get minus y squared over b squared. Right, that stays there, is equal to 1 minus x squared over a squared. And then let's see, I want to get rid of this minus and I want to get rid of this b squared. So let's multiply both sides of this equation times minus b squared. Right, if you multiply the left-hand side times minus b squared, the minus and the b squared go away, and you're just left with y squared is equal to minus b squared. And then minus b squared times a plus, that becomes a plus b squared over a squared x squared. We're almost there. And then you get y is equal to, and I'm doing this on purpose, the plus or minus square root, because it can be the plus or minus square root, of, and let's switch these around just so I have this term first, the positive term first. B squared over a squared x squared minus b squared. Now, what is this? You said, Sal, you said this was simple. I'm solving this. This looks like a really complicated thing. But remember, we're doing this to figure out the asymptotes of the hyperbola, just to kind of give you a sense of where we're going. Let me do it here. I'll do the other. Well, actually, I want to do that other hyperbola. So a hyperbola, if that's the x, that's the y-axis. It has two asymptotes. And the asymptotes, they're these lines that the hyperbola will approach. So if those are the two asymptotes, and they're always the negative slope of each other, we know that this hyperbola is either, and we'll show it in a second which one it is. It's either going to be, it's going to look something like this, where as we approach infinity, we get closer and closer to this line and closer to that line. And here, it's either going to look like that. I didn't draw it perfectly. It never touches the asymptote. It just gets closer and closer and closer, arbitrarily close to the asymptote. It's either going to look like that, where it's kind of opens up to the right and the left, or our hyperbola is going to open up, up, and down. And once again, as you go further and further, an asymptote means that it's just going to get closer and closer to one of these lines without ever touching it. But it'll get infinitely close as you get infinitely far away, as x gets infinitely large. So in order to figure out which one of these things is, let's just think about what happens as x becomes infinitely large. So if I draw, so as x approaches infinity. So as x approaches infinity, or x approaches negative infinity, so I'll say plus or minus infinity, right? It doesn't matter, because when you take a negative, this gets squared. So this number becomes really huge as you approach positive or negative infinity. And you'll learn more about this when we actually do limits. But I think that's intuitive, that this number becomes huge. This number is just a constant. It just stays the same. So as x approaches positive or negative infinity, as it gets really, really large, y is going to be approximately equal to, well, I don't want to do that. Actually, I think that's congruent. I think this is, I always forget notation. Approximately, this just means not exactly, but approximately equal to, when x approaches infinity, it's going to be approximately equal to the plus or minus square root of b squared over a squared x squared, right? And that is equal to, now you can take the square root of this. You couldn't take a square root of this algebraically, but this you can. This is equal to plus or minus b over a x. So that tells us essentially what the two asymptotes are, where the slope of one asymptote will be b over ax. You could view that as positive b over ax, and the other one would be minus b over ax. And I'll do this with some examples, so it makes it a little clearer. But so we know what the asymptotes look like. It's these two lines, right? Because it's a plus bax is one line, y equals plus bax. Let's say it's this one. This asymptote right here is the y is equal to plus b over ax. I know you can't read that. And then the downward sloping asymptote, we could say, is y is equal to minus b over ax. So those are two asymptotes. But we still have to figure out whether the hyperbola opens up to the left and right, or does it open up and down? And there, at least, there's two ways to kind of do this. One, you see, well, this was an approximation. This is what you approach as x approaches infinity. But we see here that even when x approaches infinity, we're always going to be a little bit smaller than that number, because we're subtracting a positive number from this. Right? We're subtracting a positive number, and then we're taking a square root of the whole thing. So we're always going to be a little bit lower than the asymptote, especially when we're in kind of the positive quadrant. Right? So to me, that's how I like to do it. I think, we're always, at least in the positive quadrant, it gets a little more confusing when you go into the other quadrants. We're always going to be a little bit lower than the asymptote. So we're all going to approach from the bottom there. And since you're there, it's going to be like this and approach this asymptote. And then since it's opening to the right here, it's also going to open to the left. The other way to test it, and maybe this is more intuitive for you, is to figure out, in the original equation, could x or y equal to 0? Because when you open to the right and left, notice you never get to x equal to 0. You always get to y equals 0 right here and here. But you never get to x equals 0. And actually, your teacher might want you to plot these points. And there you just substitute y equals 0. And that you could just look at the original equation. Actually, you could even look at this equation right here. Could x ever equal 0 if you look at this equation? If x is equal to 0, this whole term right here would cancel out. And you'd just be left with a minus b squared, which is you're taking b squared and you put a negative sign in front of it. So that's a negative number. And then you're taking the square root of a negative number. So we're not dealing with imaginaries right now. So you can never have x equal to 0. But y could be equal to 0, right? You could set y equals 0, and then you could solve for it. So in this case, and actually let's do that. If y is equal to 0, you get 0 is equal to the square root of b squared over a squared x squared minus b squared. You could square both sides. You get b squared over a squared x squared minus b squared is equal to 0. I know this is messy. So then you get b squared over a squared x squared is equal to b squared. You could divide both sides by b squared, I guess. You get a 1 and a 1. And then you could multiply both sides by a squared. You get x squared is equal to a squared, right? And then you get x is equal to the plus or minus square root of a. So this point right here is the point a comma 0. And this point right here is the point minus a comma 0. Now let's go back to the other problem. I have a feeling I might be running out of time. So notice that when the x term was positive, our hyperbola opened to the right and the left. And you could probably guess from deductive reasoning that when the y term is positive, which is the case in this one, we're probably going to open up and down. And let's just prove that to ourselves. So let's solve for y. You get y squared over b squared. We're going to add x squared over a squared to both sides. So you get equals x squared over a squared plus 1. Multiply both sides by b squared. Y squared is equal to b squared over a squared x squared plus b squared. Got to distribute the b squared. Now take the square root. I'll switch colors for that. So y is equal to the plus or minus square root of b squared over a squared x squared plus b squared. And then once again, I've run out of space. We can make that same argument that as x approaches infinity, as x approaches positive or negative infinity, x approaches positive or negative infinity, this equation, this little constant term right here isn't going to matter as much. So you're just going to take the square root of this term right here, which is essentially b over a x plus or minus b over a x. And once again, those are these same two asymptotes, which I'll redraw here. That line and that line. But in this case, we're always a little bit larger than the asymptotes. We're always a little bit larger than the asymptotes. Especially in the positive quadrant, that tells us we're going to be up here and down there. And another way to think about it, in this case, when the hyperbola is vertical, or it's a vertical hyperbola where you're always it opens up and down, you notice x could be equal to 0, but y could never be equal to 0. And that makes sense too, because if you look at our original formula right here, x could be equal to 0. If x was 0, this would cancel out, and you could just solve for y. But if y were equal to 0, you'd have minus x squared over a squared is equal to 1. And then you would have, if you solve this, you would get x squared is equal to minus a squared. And we're not dealing with imaginary numbers, so you can't square something and you can't get a negative number. So once again, this would be impossible. So that's the other clue that tells you it opens up and down, because in this case, y could never equal 0. Anyway, you might be a little confused because I stayed abstract with the b's and the a's. In the next couple of videos, I'll do a bunch of problems where we draw a bunch of hyperbolas, ellipses, and circles with actual numbers. See you soon.